Okay, so this is the start of chapter 5, and chapter 5 will be about mass, Bernoulli, and energy equations. So those are the three main topics: mass, Bernoulli, and energy equations. And for the first lecture, this lecture, I'm going to talk about an introduction to mass balance, and later on, I will talk about conservation of mass. So let me start to introduce the subject, and I will read the slides with you and explain them to you. So you're already familiar with numerous conservation laws, okay, such as the laws of conservation of mass, conservation of energy, and conservation of momentum. And conservation of mass and energy will be discussed in this chapter. Conservation of momentum will be discussed in chapter 6. So historically, the conservation laws are first applied to a fixed quantity of matter called a closed system. So closed system was, let us say, studied first, which is, or just a system, closed system, or just a system, and then extended to regions in a space called controlled volumes. So closed system, you remember in the past we talked about closed system and we called them what? Controlled mass. And we talked about control volume, or we call it open system, if you remember. We discussed this in chapter 2, I believe. Now, for closed systems, the conservation of mass principle is implicitly used by requiring that the mass of the system remains constant during the process. For a closed system, ضمنيا implicitly يعني ضمنيا there is no mass entering and no mass is leaving, so just the mass in the system will remain constant. It is not going to change. However, for control volume, which is an open system, we know that mass can cross the boundaries, can go in and out, and so we must keep track of the amount of mass entering and leaving the control volume. So I want to know how much mass is entering and how much mass is leaving. We want to keep a track. نحسب. So the amount of mass flowing through a cross-section per unit time, is called the mass flow rate and is denoted by M with a dot. Okay, we know this. Mass flow rate is denoted by M dot. This is a dot. And this dot, okay, this dot, the dot over the symbol is used to indicate time rate of change. Okay, if I have M with a dot, then I'm talking about the rate indicate the time rate of change of the variable itself. So a fluid flows into or out of a control volume, usually through pipes or ducts. So usually the flow will go inside or outside the system through a pipe or a duct. What's a duct? A duct is just any shape of, let me say, a pipe. So a duct can be, this shape where the fluid is flowing through, or it can be this shape that the fluid is flowing through. So pipe is circular, duct is any, let us say, conduit that is not circular, where the fluid is flowing inside or outside. Now let me start by trying to get an equation for the mass flow rate I want to derive. So the differential mass flow rate of a fluid flowing across a small area element dAc in a cross-section of the pipe is proportional to dAc itself. So suppose I want to know how much mass is crossing those boundaries. Okay, so I have this as my control surface. This is my control surface here. So I'm going to choose a small area dAc. Okay, differential area dAc, and then I have a fluid who is crossing this dAc. This is the fluid crossing here, and the density of this fluid is just rho. Okay, the density is rho. And then I have a component of the velocity which is normal to the area, to the differential area, and this component is called Vn. the normal component of the velocity. So this is the velocity, which is this thing here, v, as you can see, v with an arrow, which means this is a vector quantity. And then there is a small n, as you can see it here, this vector n. This is called unit normal, which is normal to the differential area. And then I will take the normal component of the velocity, which is Vn, as you can see. And this is Vn is not a vector. This is not a vector. This is just the normal component of the velocity vector. So let me again say what is in there. I just explained it. Now I will read the slide with you. So the differential mass flow rate of fluid flowing across a small area. So I want the differential mass flow rate. This is what I want. And I have the differential area, dAc. I have the fluid density rho. I have the component of the velocity normal to dAc, which is called Vn. Then what will be the differential mass flow rate? So if I have those, if I have Vn, which is the normal velocity, I have dAc, which is the differential area, I have the density of the fluid, then how can I get the differential mass flow rate? How can I get this? Now the differential mass flow rate is equal to the density times the normal velocity, density times normal velocity times differential area, dAc. Okay, and this is delta, means the differential mass or the change of mass, differential mass. You can check by just checking the units. Density is kilogram per meter cube, Vn is meter per second, dAc is meter square. Okay, so meter cube cancel meter cube, and I have kilogram per second, which is mass flow rate. Okay, which is mass, so it is dense, so differential mass, density, normal velocity, differential area. Now, suppose someone would say, yeah, but I don't want the differential area. I don't want the differential mass. I don't want just the mass that's crossing this area here. No, I want the mass that is crossing the whole, let us say, control surface. So what to do then? What to do in this case? In this case, then the mass flow rate through the entire cross-sectional area of the pipe or duct is obtained by integration. So I can take whatever I've got before, which is, let us say, which is this or that, and I can integrate it. So if I want the whole thing, if I want the whole mass crossing the area, not just the differential area, the whole area, then I will just integrate for the whole area. Suppose this is the whole area, something like this. So m dot now is equal to delta m, and this is integrated for the whole, area. Okay, this is integrated for the whole area. So m dot is equal to integral AC rho Vn dAc. Okay, m dot is equal to integral AC rho Vn dAc. This is the mass that is crossing the whole cross-sectional area of the control volume. Okay, now, so let me just go through this slide. So we'd like to express the mass flow rate in terms of average values over cross-section of the pipe. So I have this integral, and I know that dealing with integrals is not something that we like. So I want to get rid of the integral as much as I can by presenting values as averages instead of having them with the integrals. So let me just go through this slide. In many practical applications, the density is essentially uniform over the pipe cross-section, and we can take density outside the integral. We are saying that the density of the fluid, usually it is constant across the area, the cross-sectional area. So there is no harm, since it is constant, I can take it outside. Okay, I can take it outside this integral. Yeah, and I'm just saying that. So m, now let me just, so m, okay, m is equal to integral AC rho Vn dAc. But if I can say that this is constant, so I just can take it outside the integral. So this is equal to integral, density AC Vn dA. See, okay? So now I got the density outside of the integral. But the question is now also one might think, why can't I get this? Why can't I get this Vn? Why can't I get this Vn also outside the integral? I want to make my life simpler. But the thing is, velocity is never uniform over the cross section of the pipe because of the no-slip condition at the walls. You know this from chapter 1 when we talked about the no-slip condition. So actually, if you look at the velocity profile in a pipe, which is shown here, you will see the following. Because of the no-slip condition, the velocity here is 0, the velocity here is 0, and the velocity at the center is maximum. So I will have this velocity profile. Okay, I will have this velocity profile. So what's written here that the velocity varies from 0 at the walls to some maximum value at or near the center of the pipe. So the velocity is changing. I cannot get it outside the integral because it is changing across the cross-sectional area. But I can define something called the average velocity. So I will take like the difference, something between the minimum and the maximum, and I will define the average velocity, the one that you see here. So how to define this average velocity? Okay, so we define the average velocity, V average, as the average value of Vn across the entire cross section of the pipe. So this is the average. This is the average of the entire Vn. So this is Vn here, this is Vn here, this is Vn there. So Vn is 0 here, Vn is maximum. So I will take the average instead of all the Vn's that I have, and then I will define it as such. So V average is equal to 1 over AC and integral Vn dAc. So you can look at this, Vn times dAc, this is volumetric flow rate, and AC is area. So if you divide volumetric flow rate over area, this will give you the V average, okay, V average. So I have this average velocity, which is defined here, because the velocity is changing, normal velocity is changing from one point to the other. So I can go back now, and where AC is the area of the cross-section normal to the flow direction. So thus I can say the following. Thus for incompressible flow, or even for compressible flow where density is uniform across the cross-sectional area, I can write this equation. So I have this equation here, m dot is equal to this, but I know that the average velocity, so you can think of this as follows. So you can think of AC, let me just change the color. So AC is going here, so this will be AC times V average. Okay, now I will just cancel it from here, is equal to this integral. So again, if I have the density outside, this density is outside, and I am left with this thing here, which is the same as that. So I can rewrite this equation as m dot is equal to rho V average AC. And by doing this, I got rid of the integral by using the average velocity, which was defined in the previous slide. So I ended up with this nice equation that you are familiar with, maybe from the thermo or from the introduction course, that mass flow rate is equal to the density times average velocity times cross-sectional area of flow. I can also define the volumetric flow rate. Sorry for this. So I can define the volumetric flow rate, which is equal to velocity times cross-sectional area. And you know what is the relation between the mass flow rate and the volumetric flow rate. You can just go and read this. This is easy. Okay, you know the relation between them as the mass flow rate equal density times volumetric flow rate. Again, I want to remind you that I said this in class. I want to remind that this small v is specific volume, which is v over m, or the reciprocal of the density. This one is the reciprocal of the density. Okay, and also I want to put in maybe a dot here, a dot here, and a dot here, because those are mass flow rate and volumetric flow rate. Okay, now this is the conservation of mass principle. Also, you know this from previous courses, that input plus generation minus output minus consumption is equal to accumulation. And if there is no reaction, then the generation equal consumption equal to 0. And if we have steady state, then accumulation equal to 0. And then you can say that rate of mass input is equal to rate of mass output. So you cannot say that rate of mass input equal to rate of mass output unless there are two conditions. There is no reaction. So there is no reaction. Okay, there is no reaction. Then generation equal consumption, and steady state, then accumulation equal to 0. So then we'll get this form of the conservation of mass principle. Okay, so again, I'm having this one, rate of mass input equals rate of mass output. Suppose I have this as my process. So I have this as my process, and then suppose I have this pipe where the input is going in, the output is going out. And if I ask you what is m dot here, what is m dot here? So it will tell me that, for example, mn is equal to rho 1 v1 a1 equals rho 2 a2 v2, which is this one is m2. Okay, I am applying just this equation if there is no reaction and at steady state. Okay, this is what I have just said. This is an easy example that I will keep it to you to solve. Very easy. So you have a conduit. A conduit is something that carries the flow. So a conduit has an inside diameter of 12 inches and 18 inches. So one here is the diameter is 12 inches, and at two here the diameter is 18 inches. Okay, and then what is required is the following. So water is flowing in the conduit at a velocity of 16.6 feet per second at section 2. So if you remember, we have drawn something like this. You are given the, I believe, the diameter here, and now you are given the velocity here. So he's asking for the velocity at section 1. He's asking volumetric flow rate at section 1, the volumetric flow rate at section 2, and the mass flow rate. So this is easy. All you have to say that this is steady flow, there is no reaction, so you have to set m1 is equal to m2, and you know that, let me just change this, rho 1 a1 v1 is equal to rho 2 v2 a2, and then you know that this is this is a circle, so the area of a circle is pi d square over 4. Okay, and then you just solve for what is required here, and hopefully you will get this solution. Please check if you can get it. This is an easy problem that you can start with in this chapter.